We are ready to start the conversation. And it's a pleasure for me to introduce my colleague Gueo Grantcharov. He's a Bulgarian. I have no experience with him when I was in Cyprus here in university because he was teaching at the university. He was attending his 5-year course. So it's a pleasure for me to introduce him. He's working in the Poisson International University. And now he will talk on the introduction on generalized geometry. Please, you have the floor.
Thank you. Thank you for this nice introduction. Thank you for the kind invitation to get to go with today. And well, this is the topic which hasn't been my main research area for my last 25 years, with a little exception. And in this case, what I will do is, in fact, to go back to history, actually, and not the one which comes from physics. Standardly, the bihermitian and generalized structures are referred to as first considered by physicists, holomorphic and Gates, which is correct as model. But the time I was involved in these questions, I was unaware of this subject. I guess I will speak without my I hope you can hear. So in these terms, my talk, of course, will be 2 parts. And the first part is like ancient history. And the second should be like more recent history. What is the current state? I believe you know still speak. I think you know. So, in a certain way, these are the first 2 of at least 3 talks on the subject. And when I say history, I mean mathematical history. The research and the topic started, at least for me, that many years ago, with the basic question. Given oriented, and this is a Riemannian metric. How many complex structures say I will write down compatible here with G, which means that GI is Hermitian, or in the terminology we used back then, I is called orthogonal complex structure. This is just to emphasize that you first choose a metric and then look for complex structures. So the other way around, actually, difference. So, out of this question, it's oh, you know very well the nice answer. When n is equal to 2, dimension 2. It's excellent correspondence, 1 to 1. One metric corresponds to 1 complex structure. Of course, here when we talk compatibility, let me write it here down clearly. This is, in fact, conformal invariant notion, so that usually the question is for conformal class. The structure compatible with this actually compatible with conformal class. And the first interesting is, well, interesting means not answer, or is when n is equal to 4. N is equal to we will have four-dimensional Riemannian oriented manifold. For subspaces, the question is, in a sense, one can answer this locally, globally, and in fact, even point-wise, it's already interesting. So let's start with some vector spaces orientation. Let's call a product. Then, again, if we have I is minus identity, and compatible, we have two choices. I could kind of use the same orientation or opposite. But in any case, I'll use that orientation later on. For the fundamental form. What one knows is that this is a two-form. It has normal. Well, in appropriate sense, one. In other sense, two, depends on how we define. And the folder is nice. Of star operator, which on two forms, which means that our space is split into eigenvectors. Now both are three-dimensional, and the elements here are called self-dual forms. There's different short forms, and elements here are called anti-self-dual. Oh, right now. So the set of these structures, which are endomorphisms with square identity, let me write it like this. Compatible. As I said, actually is the union of two mean spheres here, where the one with plus is in fact the unit sphere of one with plus, and the same is for minus. In particular, the positive oriented structures to be identified with two sphere. or CP1, and same thing. Now, because we are asking about the number of possible compatible structures on a manifold, this is like the set of our linear compatible structures. I mean, one can describe this in terms of spinors. One can describe this also in a little more familiar for the right geometers way, because if you complexify the space, of course, complex structure means it's big complexified space into 1, 0, and 0, and 4 vectors. If you complexify the metric, this means one has a complex quadrant in a 4-dimensional complex space. And a compatible complex structure corresponds to a 2-dimensional linear subgroup sitting inside this quadrant. And you assume that the metric is coordinate and determine the max quadrant. And as you know, this set you can actually projectiles. And if you look at the 4-dimensional complex space, you can consider the 3-dimensional projective space. The quadrant, as you know, is actually P1 times P1. And fixing one point, the description of this S2 is actually the parameterization corresponding to the other P1. It's one point. One of the P1s corresponds to parameterizing the structure, the complex spaces, for which this is the corresponding isotropic space. Now, this approach has one advantage, for which I probably will not talk about, the relationship. This approach by complexification is irrelevant with respect to the signature of the method. And in particular, one can check the same way through complexification and this kind of lines in a quadrant. What happens if you have not positive star product, but let's say split signature? Clearly, Lorentzian signature in 4 dimensions is a metric which do not admit compatible structures, because you have only one vector of norm 1. And if this is a geometry, no, it's okay, geometry, you need 2. So you don't have 1 free signature, you have 2. But nevertheless, in 2-2 signature, the problem is your twistor spaces are not the whole sphere. So some elements in the sphere around the equator actually correspond to real isotropic spaces, because you have also real isotropic spaces in positive signature example. Real isotropic spaces. But so in these terms, the twistor spaces not the corresponding parameterization actually is not the sphere. But this is only the basic linear algebra here. And another part of the basic linear algebra, which comes out of the geometry of the sphere, is like this. Suppose that we have 2. Let me write plus and minus. No, I will write 1 and 2, and then I will change to plus and minus for the here. So suppose that we have 2 compatible complex structures. And assume that they are not a cosine, because otherwise it's going to be trivial. Then we have the 2 options. First, either I1 I2 are opposite oriented. And this happens only if they can use. Or they have the same implementations, and this happens in only. I apologize to everybody who was really involved yesterday in the talk. Of course, I'll start with quantifier. I'm not eliminating the quantifiers, just so you know, please. Don't blame me. Yes, please. So exists number between 1 and 1, not 1 and -1, for which this property I think this comes out of this is to look at spinor representation and compare it with quaternions, because this is what happens with imaginary quaternions. Or the basic so. But I'll use both. Well, I'll use both. What happens. And for example, if GSP is 0, and these two structures form something called hypercompass, so behind the hyperkähler in the geometry later. Now, suppose that I would say that in fact, reasonably nice picture, geometric one can get it on such a 6-dimensional vector space. Because the parameterization there is actually union of 3 complex objective spaces. In higher dimensions, this set, the two sets here with positive and negative oriented structures, well, depending on the dimension maybe, well, I would say admission symmetric spaces to refer to the thought by linear thought. I think in algebraic geometry they're called spinor varieties. So they are basically, again, objective algebraic varieties cut out by quadrants, as far as I remember. Now, here, if we start with, if we go back to the space, then what we can build out of this picture is we consider this is the bundle of self-dual forms of unit length. Unit length. Now, this space is called twistor space. Now denoted, well, one of the realizations, but I apologize, I'm not using X for variety of magnitude. I'm using K for magnitude. X will be vector. And this is called twistor space. And the reason it's interesting goes back to the approach of Penrose in the 50s. I think I'll first consider that And this is the space which parameterizes the pointwise compatible complex structure. What I mean is, at each point of the end, this is precisely the space of I, which are in homomorphisms here, or identify, I guess I should say, with complex and compatible. And I'll write down for positive orientation. So this is actually parameterization of pointwise complex structures, not local, not global, not clear. But the use for that comes out of the existence of topological almost complex structure, whatever. Now, in particular, the first thing to notice is any almost complex structure, almost emission structure, is fixed on any section. Basically, but not this was right down again. Now, main point is that this space has, I'll not write again existence, but yes, there is topological almost complex structure. I'll write down A, CX. Yes. So the deviation, which again, in a certain sense, was known by Penrose, but explicitly was studied by people, and I think 79 or 8. Just to give you some idea of attention that is very good. And the complex structure, almost complex structure, looks like this. So suppose that you take the Levi-Civita dimension for the Riemannian metric, then the tangent space which is in fact a bundle of unit spheres in number 2, which is again associated with the principle of holomorphic bundle, can be split horizontal and vertical parts. That's the bundle. Now, the vertical part is identified which is the fiber of this projection. Okay. Because the fiber is to sphere. Of course, this is canonical. And then the PhD Zinger or this complex structure now. So J complex structure. These two are both invariant, so this is in fact a complex structure of the sphere identified with one, the canonical one. And the tautology comes from the next one. At the point P on the horizontal space is actually a complex structure given by P on Tn identified with the horizontal space. Where I'll explain here a little bit more. So, right. P, every point, this space is a complex structure on the base of this vibration, of this point. And for appropriate point P, horizontal window, this complex structure is simple. Step forward. In particular, one way to imagine is we have fibers, and on the fiber the structure is fixed. But then we get horizontal space. And in the horizontal spaces, the structure actually varies and changes. In particular, phi is not holomorphic projection, even if the base has almost no space for any possible structure in the space. Usually, the standard description for crystal spaces and main application recently is for, let's say, hyperteller manifolds or hypercomplex, which do have holomorphic projection, but this is not. Holomorphic projection for crystal spaces of hyperteller actually is on CP1 onto the fiber, because in this case, for hyperteller, this bundle is triggered for we have natural projection on the second factor, and it is one. Now, the main point for this lecture, of course, the first result is if you have almost complex structure, you want to know is it integral or not. And to discuss the integrability, I need to say some words about this to be the curvature x, y, z are vectors. And now, because this curvature relates to the next curvature, then what happens is that R, because of the symmetries, defines also an operator from by this formula. I'll not try to write curly and straight R. I'll use one and the same method. I'll hopefully from here will be clear. when one extends the metric onto the vector. This is how it works. This is symmetric. Now, for this horizon, and this is typically dimension 4 on the picture in differential geometry, standard, the operator R, when we consider the split, which was before, is this block form where each of this is three-dimensional because this is dimensional. So this block here is 3 by 3. And the way I'm going to write is well, where B is a map W plus minus are mappings from plus minus to themselves. Now, the interesting part of the curvature theory is that these W's and B kind of encode properties like B, an appropriate form corresponds to the rich tensor traces. So in particular, metric for dimension is Einstein, if this is 0 together with this. But the one portion which actually is interesting for theory here for compatibility are the two W's. Usually W plus and minus are called self-goal and bisexual well. And if one of them vanishes, the metric is called half-conformally flat. Because the sum of the two corresponds to the power tensor, and vanishing the power tensor is equivalent local to conformal flat metric. So with this kind of basic introduction, I'm going back to that Mr. Space. And the Fichten-Zinger result is that this is integral. And this half, the positive half of the vowel tensor vanishes. In this case, G is called anti. So, well, the theorem there, in general, the reason for the crystal space construction in popularity is coming from this part, looking for metric with this property, or the other, which is self-duality. And original construction, in fact, is for structures with opposite orientation. Here, I'm looking, if you remember, that theology was plural, parameterizing all of the structures. Dimension 4, the structure and its opposite are both on the same orientation. Typical, but in general, self-duality was, and in certain sense, theory is kind of the basic topic in differential geometry and construction of this metric. That's a big issue. That many years ago, I want to explain. I still feel things and all here, and Ernesto doesn't come. So yeah, I kind of can speak about this ancient history more. And In this terms, self-duality, I guess I should mention, is actually related with mostly the so-called integrable systems. But in fact, about self-duality in split signature, where the relation is more direct, including things like different type of self-duality equations, which are not necessary for the metric, but for various bundles on complex surface are equivalent to stability, polystability of the bundle, or hermitian metrics. And the fact that this type of equations also reduce to many of the known integral systems, like orthorhombic, KP, and others, was kind of the main one of the main motivations behind the self-duality research in general. And it still goes, but mostly a lot of for the split signature. Now, here, before I go to more formulas, this is differential geometry top, which means a bunch of formulas usually anyway. Before I go a little more into the geometric picture, which is involved in the crystal space. Now, if or maybe I should say that this is kind of a basic property, and I cannot say maybe it's the same paper properly to quote. Now, this is almost complex structure. This almost complex structure, considered in this geometric way, is integrable and only if this image here is complex in terms of or invariant under this. This is on one side. On the other side, integrability of complex structure, of course, it's on its own hard condition. But when it is for orthogonal complex structure, since this is compatible, this is one of the properties, and if this is compatible and positive, assuming, but well, not positive, this is compatible, then this is integrable. Of course, this is structural matter. Okay. This integrable, even though the domain extended vanishes or something, but in terms of connection, which is that, you can only if looks like this. This looks a little stronger. From here, it easily follows that U10 is involutive distribution, but it's a little stronger. Nevertheless, it's equivalent because it's compatible. And from here, follows very easily because these are, after complexify, these are all isotopic spaces. That's one of the interpretations of orthogonal complex structure. So from here, it follows that we have this curvature condition, which is like first integrability condition for almost complex structure. Why is this integrated? Because, of course, this is local. This is local. Integrity is local. This one is already pointwise. It's a tensor-like condition, and one can check. And That's how, for example, it's relatively easy to check that if you are looking for complex structures from the sixth sphere, it's a very normal problem. Once you impose some compatibility with the method, because it's kind of easy question already. But in these terms, this is actually fourth order equation in G1 for it page either. And clearly, if I is integrable, then for if and only if minus I is so integrable structures actually very there already. And we are still looking at the answer to this initial question and how many we have. Now, out of that, we can give you the answer locally. No, actually, point-wise.
From the point of view of partial differential equations, this PDE is easier to do.
Which one? The integrability?
Yeah. It's more or less like the same as
A little bit, yes. It's well, it's easier only because you take more of the break stage. Integrability is really very, very unknown. As long as the question, in my opinion, this six-dimensional sphere question is really curious. You have very few conjectures with more wrong proofs than the dimensional sphere, but you have no other where actually the wrong proofs are split in equal. Half of them for existence and the other half for non-existence. So in these terms, I would say integrability of complex structures because that's like the base. Out of this, you can build up a really strange complex structure on CP3. Not just one kind of really strange one. If you could do it. So basically, integrability altogether really hard. Integrability in terms of compatibility is a little better.
But
Not necessarily all the right extension.
But you have some freedom about the choice of the initial length.
Oh, yes.
And this should work from your side. Play with your word.
That's the whole point. I mean, if you have so if you get to generic metrics, this curvature condition of problem cannot be satisfied for any function. Because it's generic. So the answer to the previous question is the following. Suppose we have an orientation, then number of I which are chicken-blockable, pointwise is one of the following four options. Generic option is 0. Because the algebraic condition already is found. I mean, if you slightly move the coefficients in this, you don't have. I mean, you have because it's equationing like one variable. CP1 is one variable. You have a solution. You don't have this part. Oh, 0. The other is 2, which means plus minus I. Well, unique curve sign. And let's say this happens if we have Fig of Gi is scalar with the scalar curvature non-zero. Not constant, just non-zero everywhere. In general, every level. And it has one compatible positive. Maybe I should write down plus. Then there is this option 4, which means plus minus I1, plus minus I2. And finally, this option of infinity, which is precisely and this is actually a consequence of this. The reason is, if you have the crystal space integrable complex, and you have this nice property that complex structure here then means complex subspace here. This we will see, I mean, at some point one goes to this Keller potentials and so on in this way. If you have complex subspace here, you know, locally, you can find this pointless here, but locally, you can find many complex subspaces which are transversal.
Just to check something, because here you mentioned that being compatible is invariant under conformal class, right?
Yes.
So, for instance, to the 2 on that cardinality, you could choose, for instance, some function by this Kasdal order stuff, like to ensure.
It's actually this local conformal Keller, but I give you an example. But yes, this is it only for the conformal Keller. You're right.
You know, I can just take on the conformal class to ensure this Keller efficiency.
It's not just Keller, it's local conformal Keller structures are known. Basic. But yes, so that's all local conformal Keller. Normally true, but it's exactly true. And in general, all of these are related with this operator. And because it's symmetric, 3 by 3, yes, and trace. It is known. And it depends on the spectrum. Meaning, if you have 2 equal eigenvalues, then the eigenvector, which is eigenform, the third one corresponds to vector. If you have all different, that is the case. If you have all 0, okay. Now, this was known around the 90s, easily. Well, it's kind of simple. And it is where the terminology bihermitian. This is where the bihermitian structure comes first from history of mathematics. Now, here, the reason I'm talking about crystal spaces is I want to give a little more geometry behind equality this case. I will start with the integral case. And I mean, there are many properties of the crystal space which I will not go into. And well, if I don't finish, I'll continue next lecture with a little bit more of this information. But here, if assume hypothetically, well, not hypothetically, if complex threefold, it's well, when I say complex, it's almost never Keller because all algebraic. Because it's known, for instance, like the one that the only crystal spaces which are Keller are CP3, which is a crystal space of the fourth sphere, and the standard six-dimensional flag, which you mentioned, so crystal space of CP2. All of us are non-Keller. They cannot be. Non-Keller is not Keller. So this is typical non-Keller geometry object, complex non-Keller. But in this case, assume that they define these two, because they are sections, two divisors. The I, which formally are one or two depends, and because minus is the same, or minus maybe what you put here, but it corresponds to minus, the section with minus. Because they're divisors, what one can use is simply by the junction formula. Now, I don't want to give many details, but there is also some property for the canonical control, because it's not restricted to every finalist or four, but it's not just that. I mean, one can say more. There are some relations. So one can use the junction that maybe I should try down here without, sorry, I think I'm forgetting the one notation. I can say about the intersection. And then this one, purely set theoretical, responds to the points B. So this is set in N, the base, for which all these corresponds to points where the two structures are equal opposite. And assume that they are actually divisors which do. There are many cases in which this is trivial. Like we have a vector structure, we have two of the family, two complex structures of the family. Of course, if it is taking 0, they are different everywhere. But if this is non-zero, the junction formula. So I started with the junction formula and assume that then this intersection defines anti divisor for both I1 and I2, and I would say up to in general, up to the divisor of R0. And actually this divisor is with plus and minus, so there is some relation. And under simple topological restriction, like suppose that we have even first Betty number, this is actually trivial. These do correspond to anti-canonical divisors. And I'm not assuming that these two structures are equivalent or anything. Just they are sections compatible and not equal to plus minus everywhere. But Now, this is under the assumption of integrability of this perspective. However, to skip the integrability, still have almost complex nature. We still have complex four-dimensional complex one subspaces, which are only integral even, but the junction formula is out the relation of the power the tangent bundle. So formally, you can write the junction formula then disregard the question exactly under what conditions and you still get the same property. So in a certain way, one sees from here that the integrability for this particular, this is the point command by condition, it's not nice. Which means that it should be related with more to the differential already. And starting from this fact, somehow knew that what we have to look for is, of course, anti-canonical divisor effect. It means existence of homomorphic. It's complex. So we knew at this point, without being aware that this is actually captured somehow, not explicitly already used, we knew that we need to look at homomorphic section of the which is effective. And from here, one looks at the differential geometry without suppose that we have two complex structures and assume that are positive for your end. Then the formulas, let's not go for me. Going to choose the formulas. Have to rewrite a little bit. The formulas it one gets, we have the two forms, and then, because this is dimension 4, the three form is always go in by the Hodge, by the lambda operator of the Taylor form, for one form. This sometimes is called Lie form. And for these forms, what one gets is, let me write down. I will not finish everything, that tells me. No, not that bad. I have this, that we have the first, and if U1n is even, we have directly is equal to 0. We have also which are useful just a second. And what one gets, what is, if we consider that and I'll write it as omega k, then this omega k is 2, 0 plus 0, 2 real form. This is dual, go through Poisson structure. No. Because holomorphic, the Poisson structure is not condition in dimension 2, it's trivial. Every 2 vector is Poisson in a sense 2, 0 vector is Poisson because the commutator of 2, 0 vector to 0 vectors is 3, 0 vector, which do not exist in dimension. This type of integrability condition for 2 vectors to Poisson is trivial. Point is holomorphic. And in a sense, there is also one more relation which gives some information why this comes out of Poisson structure. Because there is a dual simplex. So I guess I'll continue with geometry next lecture, and then I'll go to the more recent basic notation. All of these become generalized.